got used up in the second step. That's an intermediate. Do we need a container of NO2? No. But we did need a container of NO to add it. You have to physically add the catalyst to the reaction. That's what makes it different from the intermediate. Artea, I'm ready now.
That was my question, actually.
What was your question?
What's the difference between that catalyst?
Oh, the difference between the two. Yeah. So you have to physically add the catalyst in the reaction, and then you get it back out at the end so it never got used. In intermediate, you didn't have to add. It was just made, but it's not a product because it got used up then. James? You still don't have a question, right? Okay. James says, nope, don't have a question. Okay. So now, hey, before we're going to do two examples of problems, I want to take you back to the equation that we talked about yesterday. Whose name goes with the equation we learned yesterday?
Arrhenius.
The Arrhenius equation, yeah, good old, what's the first name?
Spiteri.
No, that's one of our physics teachers. Svante Arrhenius, right. Why'd you forget Svante?
Spontaneous Arrhenius.
Is that the Arrhenius equation?
Totally.
Maybe.
Why not?
That used to be, according to Arrhenius, that was Z times P, and then people say, well, that Z and P is really hard to measure and define, so it was taken out and just left as A. Now, I've got to say a few words about that A. A is called the frequency factor. It has to do with the number of collisions, I should say the frequency of collisions, and the number of them that have the right orientation. Now, I'm going to write this out. Number of collisions with proper orientation. That's all built into A. Also, the frequency of the collisions. What affects the frequency of collisions? Temperature does, that's true. Temperature is already part of this equation. So we're going to leave temperature off. But yeah, we're talking about for gases. If you take gases and you squash them down to a smaller volume, then they're under a higher pressure and they're going to collide more frequently. So pressure is going to affect the gas frequency of collisions. What about if you have solutions? The reacting things that are in solution. The concentration will affect the number of collisions. What about if you have solids? Can you speed up a solid reacting?
Grinding them.
By grinding it up into smaller pieces. And so what does that affect? That affects the property we know as surface area. Because if you take a solid and grind it up, you're exposing more of the solid to the other reactants. You're going to have more frequent collisions with a solid if it's ground up. Rather than if it's in a big block, the particles on the inside can't contact anything. So yeah, for solids, the surface area. It's good to know that. But that A is not just a pretty little symbol. Right, Anna? A for Anna, right? But it has, depending on what the reacting substances are and what condition they're in, A will affect the speed of the reaction.
A for the A, I will never get in this class.
You can never get the A.
It is an honorary symbol, isn't it? All right, so I wanted to talk about, yes, sir?
Will we ever have to do exponential graphs of that?
Yeah.
Please say we won't. Okay, good.
Thank you.
You said there were 4 hours.
I think we're going to have to use this equation. That's why I wanted to talk about it some. Let's think. Now, please don't fall out of your seat when you see the problem.
Okay.
And don't write it down. I'm giving you the number of the problem in it. This is not one of the assigned questions, but it is. I was afraid of that. But it is just after one of the assigned problems. So this is very similar to some of the ones that we're asking you to do. So let's take a look first and then see if we can work through it. The activation energy for a reaction has changed from 184 kilojoules to 59 kilojoules at 600 Kelvin by the introduction of a catalyst. So, are you okay with that so far? A catalyst has been added. When it was not catalyzed, it had an activation energy of 184. Now that it's catalyzed, it's only 59. Did the catalyst help, you think, to speed the reaction up?
Yeah.
I'm thinking so. The higher the activation energy, the slower the reaction is going to go. So this thing has lowered the activation energy. The uncatalyzed reaction takes about 2,400 years to occur.
Ah, that's great.
2,400 years?
Tiny bit
Can you
unfeasible.
make it into
Maybe
How long is
tonight
2,400 years? Grandkids?
like
That's not even 100 years.
great.
We're talking about 2,400 years.
24 grandkids.
24 generations.
24 generations.
No?
Yeah.
It's a generation, about 20 years, 20, 25 years.
Ah.
72.
Because you can easily get 4 generations in 100 years, right? It's 2,400 years. So, I mean, this is obnoxious. This is a ridiculous reaction. So, yeah, it's not like we're going to start this reaction in a special family vessel, right? And say, okay, now when this reaction's over, I want you to remember all the people that came before you. Forget it. You have ungrateful kids that probably just break the container or whatever, right? All right. So the question is, how long, now that this reaction has been catalyzed, how long is it going to take? Hopefully not 2,400 years. We're comparing the speed of the reaction when it's catalyzed to when it's not catalyzed. Mathematically, what do you do when you're comparing things?
Proportions.
Right, set up proportions. Ratios and proportions, right? Isn't that a mathematical comparison as a ratio? All right, so let's do this. Let's say K of the, it doesn't matter which, I'm going to make it easier for you though, and put the, oh my gosh, let's put the uncatalyzed on top, divided by K of the catalyzed on the bottom. So it's just comparing the speed of it when it's uncatalyzed, the speed when it's catalyzed. Well, using the Arrhenius equation, since K is equal to this thing, that would equal, this ratio would equal A times e to the negative EA over RT of the uncatalyzed over A times e to the negative EA over RT of the catalyzed. How do you like that? Nice. Do we know some of those terms in there? I think so. All right, now, here's a little bit of a rub. You're given the amount of time the reaction takes. Is that the same as K?
No.
How is it related to K?
Oh, yes. It's linear.
What, Nick? Inversely related to K. The longer the time of the reaction, the smaller the K. Right? When, what? If the reaction is slow, what would you say about the amount of time that it takes?
Less time.
A lot of time.
So K is small if the reaction is slow because the rate is small. The time is long or big. So when you have 2,400 years, you've got a long amount of time. What does that say about K? So the time component is big, but K is very small. They're inversely related. Here's another way of looking at it. The unit on K, it varies with the order, right? The order changes K. Where do you see time, though, in all the Ks?
At the bottom.
In the denominator. It's always 1 over seconds or 1 over molarity seconds, right?
Yeah.
Or molarity per second. So time's always at the bottom. So when I'm comparing the Ks, I need to put the time actually in the denominator. And so that's going to look like this. The K of the uncatalyzed is not 2,400 years. It's 1 over 2,400 years. The amount, or the rate of K when it's catalyzed, we don't know how much time that takes. We'll call it 1 over X. What do you think of that?
30.
You okay with that? So that's my ratio of the Ks, because K is inversely related to time. All right?
So,
Now over here we don't have any funny business. Yeah? we don't know what the order is. I brought up order just to say that no matter what the order, when you find k's unit, it's always got time in the denominator. Because k always has time in the denominator.
It's a fact that, K and time are like inversely.
Yes, right. And you were given time, so the time goes on the denominator of k. Okay? K?
K.
That was dumb. All right. Now the right side of the equation. One thing that was very nice in the problem, the Zoom dolls had a moment of being nice.
Wow.
What does it say about A?
For the first time and forever.
A is constant. That means we can cancel it out.
Yeah.
That's handy. I got this, Kathy.
They won't be as nice.
Whereas handy dandy is your khakis.
Okay. So now we're going to start plugging numbers in, and this is going to get just a little bit ugly. It's like a Shar-Pei, though. Shar-Peis are kind of ugly, but we like them anyway.
Shar-Pei Evans.
What is a Shar-Pei?
You take out your handy little phone and Google image Shar-Pei.
Then we get that girl.
I think it's S-H-A-R-P-E-I.
Yeah, you're from. No, she's not from.
All right, now stop, please. Let's plug our numbers
Did she have her
in.
own show too? Oh, yeah.
E
Her own.
to the, now remember, the numerator has the uncatalyzed, so the activation energy when it was not catalyzed is 184, so it's negative 184.
Ew.
Okay,
Yeah, Ashley took 0 from.
I'm just plugging numbers in. I know that I just threw a lot of you off. Look at all the people with their phones out. Fine.
One.
Anyway,
Wait.
184 over the RT. Now, what's the unit on the activation energy? It's kilojoules. What do I have to plug in for R?
8.31.
No, not 8.31.
8.31 times 10 to the third.
0.0 negative third.
Negative
0.00831.
My bad.
Thank you.
Same thing.
And then the temperature is given to you at 600 Kelvin. Divided by E to the, here we go again, negative activation energy when it's catalyzed, which is negative 59. Why is it negative? Because that's the formula, right there. Activation energy is always positive, Shri.
Stop confusing us.
So you have to take the negative of that number. It's just funny, Shri, you were asking that at the same time I was thinking that. Because I said negative 59, and I knew that I said that too fast, and I was going to say, and when you asked, I was tuned in. Okay, how do you like the algebra here?
Ew. It's fine.
Not very.
Okay, we have some Shar-Pei algebra. I kind of like doing this. This is cool to me. So, how do we simplify this thing? Lena? Say it again louder. You got it? How do we simplify this side?
Do math.
Just do math. Right. Okay, now, can we talk about simplifying this thing? To simplify it, you have e to a power divided by e to a power. What are the rules for when you have a division, things like that? When the base is the same, keep the base, subtract the exponents. Yes? That's true. So simplifying is not bad. Negative 184 over 0.00831 times 600 minus all this is on the power of e, negative 59 over 0.00831. Sorry about my small writing. Okay, so it's this. So now you can subtract those fractions, keeping the denominator, negative 184 minus negative 59.
Negative 100.
I want to give you a moment. Do this problem. If you've done it right, you're going to look at that and say, that can't be right. That can't be right.
Because we never get
No matter how correct it is, it can't be right.
This one might make it down. Mohammed?
I'll do the math.
Or yeah.
For the K what? whatever this numerator is going to cancel out because it's one of that over one of